Hello everyone. Hello Charmian. This work is entitled Assessment of Deep Transfer Learning for Speed Transmission Index Prediction. I am Heriberto Oliveira and this work was advised by Professor Paulo Henrique Trombeta Zanin. Introduction. The acoustic comfort in classrooms, it is a fundamental element that interferes with the teaching-learning dynamics. Speech intelligibility is measured using the Speech Transmission Index, STI. However, measuring STI it is a complex and requires expensive instrumentation. There are plenty of predictive models of STI that use the reverberation time as a regression variable. Still, these models do not consider the spectral effects of the room's impulsive response signal as well as the spectral content of the background noise. This paper aimed to model STI through the one deep dimensional convolutional neural network. The neural network had two inputs. The first, the simulated impulse response via the virtual sources method with 10,000 samples, and the second one was the background noise with 564 samples. The training target was the predicted STI provided by the standard. In addition, the deep transfer learning was applied. The deep transfer learning aims to optimize the previously trained neural network model with simulated data and transfer the generalization to the in-situ measurement data. So the objectives were use the deep one-dimensional convolutional artificial neural networks to provide a model that used the entire signal captured from the room's impulsive response. And the second one was to optimize the deep neural networks with the deep learning transfer learning heuristics. So the basic model for predicting the STI was followed according to the ISE. The STI it is measured using the modulated reduction factor, and it is easily predicted using this equation where we have the reverberation time and signal to noise ratio. The signal to noise ratio it is important, and here we have the background noise. In this work, the background noise was estimated using the data acquired from a data set provided in the internet, which was consisted of sounds, environmental sounds of different spectral contents. The simulated room impulsive response was made using the image source method. So our dataset was composed of a sample of size 10,000. Basically, it was generated 1,000 impulsive responses from rooms which varied its volume from 120 cubic meters to 1,000 cubic meters. The reverberation time was also considered as random, and its values were between 0.3 to 2 seconds. So for a great training strategy, we used a Gaussian distribution. So following both the room impulsive response and the background noise, they were standardized by the spectral content by means of the spectral density. This process was better shown in the figure. We had two inputs, the power spectral density and the room impulsive response. Both of them were transformed by the power spectral density, followed by the application of the one-dimensional convolutional neural networks. This process was made basically from the low-level feature extraction to the high-level feature extraction, and after it was passed through a traditional machine learning algorithm using the multi-layer perceptron and a classification problem based on these two impulses, the RIR and the BGN, and after we get the output. So the deep transfer learning was mentioned before. The basic use of the deep transfer learning was we have a set of simulated room acoustic impulsive responses, but we not used real measurements. But we have a set of real measurements, and we did apply transfer learning that aim to use the real measurements as a proxy to the model to gain knowledge. So we used a metric called maximum mean discrepancy as shown in the above equation. The basic process we can show as following. As we have created a room, simulated its impulsive acoustic response and captured the signal, followed by a standardization of the signal. So we did have a time domain signal after we transformed to the octave bands, and after that we transformed the signal. As mentioned earlier, we tried to measure all of the content distribution which followed a Gaussian distribution regarding the STI value. This distribution is in alignment with the literature. And after we applied the power spectral density to both inputs, and after that we proceed to the training. The training was successful, meaning that the loss was low while the accuracy of the classification problem was assured by means of the confusion matrix as shown in the figure B. The accuracy was above 0.9, which is a great value. And also we did apply transfer learning. Transfer learning was applied using the variational autoencoders. Here it is shown the variational autoencoding latent space for the training, and here it is shown the latent space for the real measurements. And making a relationship between these two distributions using the deep transfer learning, it is possible to construct a relationship based on the equation showed previously, the maximum mean discrepancy. And using that equation, we came with a nice relationship, which is basically as follows. We did have a distribution, for example, for a STI value of 1, this is the reference curve, and for the same value for the other curve, but for the real measurement, this was the predicted variable. So basically, with this matching between these curves, we could predict the STI from a room based on the simulations, and also we could apply the transfer learning to predict the results. I have to mention that these were preliminary results, and the work was good in showing that we can indeed predict the reverberation time using predict the STI using the reverberation time, but not the reverberation time, but the entire time signal. So I would like to thank the attention of all of you.